All righty. So, turn off your hair dryer. Just kidding.
Um,
Yes.
Hi, can I actually talk to you about possibly section 7.3, or ask you a question on, or
Yeah, we can start there.
all right. I was wondering exactly how would number 5 be done, because I did it and I didn't get the exact answer, so I was wondering exactly what I did wrong.
Okay, number 5.
Yeah.
All right. So that's the curve y equals 3 minus x squared. So it hits here at 3. Now it's going to hit down here at square root 3. So that might be a possibility. You revolve it around the y-axis and you think up and down, then you'll get shell because your strip will be parallel. But the volume will be 2 pi, the integral, and you'll have the radius function and you'll have the height function. And because the strip is up and down, it will be dx. So you'll have the integral, at least we'll have the x bound 0 and 3. Radius and height. The radius is always x unless you move the axis of revolution. So if it's y, the y-axis is the revolution, then the radius would just be x. The height will be governed by the curves. In this particular case, the curve is 3 minus x squared and 0. So 3 minus x squared. So at least for the setup, that's it. If you got the setup, then you're okay. If you didn't, then we need to fix that. If you got the setup and worked it out and you didn't get the right answer just because you had some integral problem.
Yeah, no, that's the thing I was wondering about. It was the x. I kept replacing it with a 3 because I thought it was a height of the function, not exactly just the
Which one, the x or the?
Yeah, the x value. The x value. I thought it was just a height of the function for some reason.
The x is the radius of the shell. It has nothing to do with the height at all. It's how far you go over to the side.
Okay, so in this instance, wouldn't be square root of 3 at all? Because I thought, because you're turning around the single y-axis here, so would that be the actual would it be the actual value or area of the or radius from the axis, or no?
It would be the radius if your strip was here. That's true. Let's go back and just conceptually see what we're doing. So here is what we're doing. If we didn't know any calculus at all, and we revolve this thing around, one way to do it with the Riemann process would be to chop this up into a bunch of strips like this. Say approximately 1, 2, 3, 4, 5, 6, 7. So now you revolve this around. I want to revolve all 7 of those things around. And so if I do, say 1, 2, 3, 4, 5, 6, 7. The first one, when I revolve it around, well, that's just going to be, it's going to look like that. There's, The next one, when I revolve it around, it's going to be, I don't know if I want to put it on here, but it's going to look kind of like, it's going to be a little bit shorter, right? Because I'm taking this second strip and revolving it around. So it's going to look like that. And the hole in the middle is actually a little bit bigger than that. If I revolve the third one around, what happens? I go a little bit wider, but I'm not quite as high. So
Okay.
I'm going to get that. And then if I keep going, that's 2, 3. What's 4 look like? 4 is going to be even wider. Maybe not that wide, but it's going to be even wider. And then when I do 5, 6, 7, and so forth, these things are going to get shorter, which means the h is going down. but the radius is getting bigger each time. I get a small radius, then I get a larger radius, then I get a larger radius, then I get a larger radius. So the radius changes depending on where your shell is. And so that's why you can't just say the radius is square root 3, because the radius depends on where you're at, this direction, and that's why the radius depends on the x position of your strip. And so that's why the radius is a function. The height, well, you could figure out all these heights by just taking 3 minus x, figuring out where your strip is located and going up. So the height is going to be governed by the equation 3 minus x. And when you put those together, you do a summation of all these things, but then you take a limit, and you end up getting an integral, and that integral ends up being that equation right there. I know it takes a while to realize that, yeah, it looks like the radius is square root 3, and it is if you were to revolve this whole thing around, get like a bullet shape. This is square root 3. This height is 3, but what's the volume formula for a bullet shape? The answer is I don't know.
Okay, so it's just in general, basically, the R value. It's just the radius from the x-axis is in general for any value, basically.
Yeah, right.
Okay.
We use the letter R now to mean lots of things. Wait, do you mean the radius is the eventual, like the overall radius of the object? Well, then that is square root 3.
No, the radius from the center of the axis.
It's right. Do you mean that it's the representative of how far away you are from the axis as you move through it? Well, that's going to be different depending on where I'm looking, and therefore it's going to be a function instead of just a number. Just look on the edge. What's the height right there? The height is 0. The height is 3 here, and then it's like 2, and then it's 1, and then eventually it's 0. So the height will change as you move through it, as opposed to the overall height of the object. One is a constant, one is a function. So you just got to get your brain right as a function. Hope that is.
So if you're revolving around the y-axis, is R always x?
Yes.
Okay.
Yeah. Right. So basically, it's kind of like, let's see. So, right, if you're revolving around the axis, maybe if the object is like here, then if you're revolving around the y-axis, then the radius will be x. If you're revolving around, say, r equals -2, no, don't write r. You're revolving around like position -2. Now what's the radius? It's x, but it's 2 more units away. So you have this additional 2 units plus whatever your x is. What happens if you're revolving it around 6? Well, now the radius is on the other side, so the radius will be 6, but you take away whatever the x-axis is. So is there a nice formula for all of this? It depends on where the location of the axis is relative to your object. I guess if you like formulas, you could say, well, if the axis is to the left of the object, then the radius will be x minus wherever the revolution axis is. And in this case over here, wait, it's minus? And the answer is yeah, it's minus because it's minus a minus, and you get x plus 2. What happens if it falls on the left? That's if it fell on the left. What happens if it falls on the right? Well, if it's on the right, then the axis is, you take your revolution axis position and you subtract x. So in this case, the revolution axis out here is 6. So it's either going to be like x if it's on this. If it's on this side, you're going to subtract x minus that. If it's on the other side, you're going to subtract the number minus that. Now, the nice thing is if you're like, ah, crap, I screwed it up, I subtracted the wrong order, then it doesn't really matter, because look at what's going to happen if you did it where this is r or it was minus r. Then in the end, suppose the answer was 10, but you got minus 10. The answer's like, well, I know it's a volume, therefore it has to be a positive number, so I probably just subtracted wrong here. Of course, at the same time, maybe you subtracted wrong there. It's like I subtracted wrong there and I subtracted wrong there, and I ended up getting a positive answer that worked out right. Oh, yeah, that's because negative and negative together become positive. So, maybe if you want to just think, always take x and subtract off your revolution axis, and your answer will either be correct or it'll be negative. And you just have to make it positive.
Cool. Thank you.
So, sir, what will be R if the x is revolving around the x-axis? What will be the radius?
Right, okay. So if you're revolving around here, suppose your object is up here that you're revolving around. So if you're revolving around the x-axis, then the answer is that the radius is going to be y. And all of your integrals will be dy when you're doing the volume. So the answer would be, the radius would be y if you're going around the x-axis. If you moved it down here to say, -3, then you have 3 more units. So my radius would be y plus 3. It's kind of like y minus a -3. If your axis was up here at, say, 10, then your radius would be, well, now I went too far beyond, so I have to go 10, but I have to take away that distance. So it's kind of like 10 total. Y is to here, and my radius is now from the axis of revolution. So you can take 10 and subtract y, you get y. So, but again, it really is just going to be either y, it's going to be y minus a number, or it's going to be a number minus y, depending on the location of your revolution. And again, if you did the subtraction the wrong way, then your answer would just be negative to the answer. Hopefully you go like, no, that's not right, it's a volume. Just change it to positive. Any others you want to do there since we're doing this before we start?
This is kind of I guess a little bit of a bizarre question, but what's the difference? But what is the real difference in terms of when to use disk method versus the washer method? Because looking over in the book, and I mean, it looks like you could use either one because you can convert either one from y to x-axis rotation.
That's true. You can use either one.
So what's the point of having two then? Why is it? What's the difference in this case? As I was looking again last night to be sure, and I just didn't see it.
Yeah. I think it'll end up being one of those things when you set up both methods. It's possible that one of your methods you're going to have to break into multiple pieces. It kind of depends on the region that you're revolving around. I think the example is suppose that here is your region. It looks kind of like that. Now, I don't care which way you revolve it, but which way do you want your strip to go? And the answer is, well, if I think about this where I want the strip to be, that's terrible. If I want the strip to be up and down, well, then I really going to have to break it into two pieces, because in this case, I have a strip here, and that's going to be governed by this lower curve, number 1, and this upper curve, number 1. And then over here, when I do the strip, I'm going to have upper curve still the same, but I'm going to have a second lower curve. So if I tried my strip, whether it's revolving one way or another, it doesn't matter. I'm going to have two integrals that I have to figure out. But if I thought about it side to side, now you turn your head sideways, you're looking at it this way, then I only have one right curve and I only have one left curve. And therefore, when I calculate the volume, I'm only going to get one integral out of this. This one's going to be both dx's, this one's going to be both dy's. So if you don't like converting things into x equals with y's, then you're probably not going to want to go to this one anyway. That's one reason to do it. The other reason is that when you do the integral, you may get some functions that do not integrate very nicely. And so it's up to a comfort level on your part as to maybe something has a square root in it. But when the disk formula has a square, you're like, I don't like square roots, but I know the disk formula has a square in it, so the square of the square root will be canceled out, and that'll be a lot nicer. So I think at this point on the test, it will be revolve this region around this axis, full stop, and you got to do the method that you're comfortable with. I don't think I'll guide you. I probably won't. I'll just say, maybe I'll say do it around the x-axis and then do it again around the y-axis. Don't work it out. Just set it up. So it'll be up to you. Yeah, why have two methods when one method works? Well, there's probably a reason. We're not just trying to make busy work for you. Sometimes you get to these cases like, how does that, I can't figure this out. But if I reverse my thinking, and I just did that this morning in Calc 3, where you end up getting, this is a little bit of foreshadowing here, you end up getting things that look like this, like a double integral. And you're like, oh, painful. But you might want to do the double integral, like a y integral and then an x integral, whatever that even means. That's Calc 3 stuff. Versus thinking the other way. One is where you're talking about the strip up and down, and the other one you're talking the strip side to side. So if you don't like the strip and you think we're going to be done with that, nope. That'll be through all the way through Calc 3 and 50Q and all this sort of stuff. Because really, that's what calculus is about. Take your thing, chop it up into little pieces, approximate the pieces, and this is technically sort of like pre-calc stuff. You can do this, chop it up, add up your answers, get your calculator out, add, make a mistake, crap, go back, start over. And we're like, oh, if we actually just took a limit process to this, then we end up getting nice things, like we end up getting nice integrals out of this. And this is really the calculus side. And this is kind of like, I don't know, the word ugly, and then this is, maybe I shouldn't use this word, but if you like math a lot, the word beautiful kicks in, and you might not think it's beautiful, but it turns out if you take mathematicians and hook them up to MRI machines, they've done these things where they do brain scans, that when they're doing these sort of nice, elegant, beautiful things, it lights up the same brain cells as it would if it's like the pleasure center. So maybe that's a little bit of it's a little too much information going on there, but anytime you're working on a subject that is really, there is some beauty to it. Somehow our brain has this reaction. Honestly, this stuff has got to be ugly. If you like things like, I'm going to take 0.09345 and then I'm going to add it to 0.063. I mean, I'm going to stop right there. That's just like, come on, that's terrible. That's ugly. But if you get over where you're like, ooh, you're getting these really nice numbers like E, and they even call this the golden ratio or the perfect ratio. These are nice, where these are like, this makes you sad and this makes you happy. So eventually. Okay, off on a tangent there. Let's finish this section off as far as we can get. We'll see, because we probably still want to have time for homework and test is tomorrow. So, and that's on not on this stuff, but we do need to get it in, so we will. So 7.5 is on work, the notion of work, which you may have seen in physics class, and then 7.6 is on fluid pressure, which you may have also seen in physics class, or heck, you might be a scuba diver and you've experienced this, or even just a snorkeler, or if you've gone in the water at all, you can feel the pressure on your ears. So how does that sort of impact? So those are the two, and they are applications of integrals, so we will get some integrals coming in eventually, very quickly. Okay, so 7.5, read this off. Work, the notion of work, and this isn't like the English word work. It means you take an object and you lift it up, you're going against gravity, you have just done work in the sense of physics. So all that means is you have some force, then you're moving it a certain distance away. And that's exactly the definition of work. So they use the letter W, and all this is, it's force times distance. So work equals force times distance. Now, before we go into all of the calculations, you've got to think about the units on these things. So what is the units of work? And it depends on whether you want to use like the English system or you want to use the metric system. So in one, sort of like the English system and I suppose the American system, is force you can really think of as like force due to gravity. So like force will be measured in pounds, and distance is going to be measured in feet. So I mean, you can make whatever units you want out of this, but the typical ones are if you take force times distance, then you get what is called a, this is called a foot-pound. If you've ever heard that before. Foot-pounds of force, and that's it. So they might write it as like feet times pounds, something like that. It looks reversed because I've got force first, but they'll write it like that. It's not foot per pound, it literally is like feet times pounds. So that's the foot pound. In the metric system, they use that force will be measured by newtons, or newtons, and the distance will be measured in meters. And so if you multiply newtons times meters, you get, not too exciting, you get a Newton meter. So that's one way to say it. You get a Newton meter. You can write it as N for newtons and M times meters. And if you don't remember what a Newton is, well, that is, it is 1 kilogram per meter per second squared. So it's like your kilograms through an acceleration will give you newtons. And then you multiply that by meters to get a Newton meter. And this, if you notice, well, I've got meters twice. This isn't, it's a kilogram per meter, or it's a kilogram meter squared per second squared is a Newton meter. And so it goes back to the basic things, right? Seconds, meters, and kilograms. Those are key parts of metric. The English system is like, foot pounds. It's just kind of ugly. We should join the rest of the world, but we're struggling. So anyway, and guess what? They call this something else. So a Newton meter, we give it a new name, and it is the letter J. So maybe you already know what's coming, but these Newton meters are also called joules. So 1 joule is a Newton meter, which is a kilogram meter per second squared per meter, or it's a kilogram per meter squared, kilogram meter squared per second squared. Yay. We now have at least our units. The answer is going to be either in joules or foot-pound, depending on which application we're going to do. So we'll start off with a small one that. So let's see. Suppose that you had, for a basic example, if you had a rock here, so just a solid thing that weighed 100 pounds, or 100, why did I write that? If you had something that weighed 100 pounds and you lifted it 50 feet off the ground, just pick a peak, pick the whole thing up, then how much work did you just do? And the answer is, well, it's super simple. It's just the force, which is 100 pounds, times the distance that you moved it, which is 50 feet. And you get 5,000 foot-pounds. So if you just have an object like that and you just do a certain amount of work to it, boom, that's it. You just multiply those two things together. So you're like, man, this section is going to be super easy. So there's probably going to be a twist coming up here pretty soon. And here we go. We like to do these kinds of problems just to show how you take this, which looks like a strip. I did that on purpose, and lifting it up, we're going to basically take a bunch of these and try and put them together. So this is an example, and if you want to read through it in the book, this is example 7.5.1, so you can see where this stuff comes from. Is you're standing on top of a building here. You're standing here, and or a cliff. It says a cliff, and it says that the cliff is 60 meters high. So now we're going to switch to the metric system on this one. We've done one in English. We're going to switch to metric here. And you have a rope. You're like holding the end of a rope here, and it is dangling down down to the ground. So you're like climbing off this cliff, and you have this rope that you want to reel in. And the way I've drawn it is you're standing here, but really it's like the rope starts there. So you have a 60-meter rope that you want to pull in. So it's a 60-meter rope, and it tells you you're going to need to do Newton meters here. So in order to work this out, you're going to need to know the density of the rope. So the density of the rope is, in this case, it says it's 66 grams for every meter. There is what it said. Now I'm just going to go ahead and convert that, because all these things you're going to have to work out of meters and meters and kilograms. Meters and kilograms. Yeah.
I just want to ask you something. So, I mean, I do technically get it because gravity's pulling the box down there, but it has a certain degree of force to it. But it just feels weird saying calling weight a form of force. It just, I don't know, seems a little odd. Is that?
Well, you probably have heard of the force due to gravity, right?
Yeah.
That's your weight.
I mean, no, I understand that. It's just, never mind, continue. I'm sorry, I'm just confusing myself at this point.
Honestly, this is one thing that is, I think when I was in school, I started in engineering, and I just took some math classes, I took some physics classes, and I got to the point where I did see what I thought was the beauty part of math. I think some people do get that. Watch these YouTube videos about really cool things that are going on. They use a lot of mathematics. Look at the spread of COVID right now. I mean, there's a lot. You realize how difficult this is to do applied math. But looking at spreads of diseases, trying to then use that information to make plans. It is difficult. But in this, I've heard in physics classes the terms Newton, joules, who else? There's so many people's names that I'm like, I don't even know what a joule is. I've seen the dude's face, but I can't get this concept of what a joule is. And they kind of use a kilogram to both mean mass and force. Or it's like there's kind of like this, which one is different? It's like between forces and masses. And my brain just had a hard time wrapping around. So when you talk about forces as being weights, I understand what you're saying. I think in English system, it does help when you say pound. You realize that is a relative term, right? If you're in space, how much do you weigh?
You don't weigh anything. It depends on where you are exactly.
What's that?
It depends on how close you are to a certain object, basically.
Okay. Suppose you're in pure space, right?
Oh, nothing. You're weightless.
Right, but you still have mass.
Yes.
Okay. So when you go to the moon, instead of 100 pounds, you would weigh what? Like, I think it's a sixth or something. So you're
somewhere around there.
16, 17 pounds. So that really is like the force that the moon is imparting on you, even though your mass has not changed. So maybe it's best to think of your mass in terms of something else, in terms of kilograms instead of pounds. And that one kind of goes both ways. So
okay.
Yeah. So when you're doing this rope thing, you do have a 60-meter rope. The density, like every meter segment in there is 66 grams. I'm going to go ahead and just convert it. So that means 0.066 kilograms per meter. Because I want to use newtons, and newtons does not use grams. It uses kilograms in here. So we have that. We also need my seconds squared. So now I'm going to have to take this idea of like this kilograms and really where's my force going to come from? I need gravity. I need my gravity. So this is, you can argue about this, what is the value of gravity? It's cool if you see, there's these maps of the entire world that's color coded based on what the gravitational force is. It is not constant. So there, if you're on the top of a mountain or you're down near the ocean, you will not experience the same gravitational force. It will be so slight that you can't tell.
Isn't there a different gravitational pull like around the middle circumference of the Earth?
Yeah, there is, I think.
That the Earth actually bulges out of it.
That's correct. Well, that's because of the revolution of the Earth. Yeah. So that's why they launch rockets in Florida and as close to the equator as possible, because you'll get that boost, the speed boost. But yeah, also because of the spin, that the Earth is actually not a sphere. It actually is. Yeah,
it's more oval-like, but still, I mean, I understand what it is. I understand because I took physics classes in high school and I understood that, but it just still seems a little odd to me at times. That's all. I do understand the concept though.
I agree.
And also, the further you're out from Earth, the less the gravitational pull. I learned that because I took physics last session.
Oh, you did? Okay, right. So you learn these things about like something like the force is equal to m.
Equation sheet.
You got it already. So it's like, what is it, like g, the gravitational thing, depending on the object. Yeah, m1, m2 over the radius.
2. No, radius. That's right, not 2.
Is it the radius cubed or the radius squared?
I thought it was squared.
Like the radius of Earth, the mass, etc., etc. So they're constants.
So, but is it r squared or r cubed? I think it's.
I don't remember that part.
Yeah. So I think we're talking about inverse cube laws and inverse square laws on this stuff. Yeah, I agree. But that really only holds for 2 gigantic objects. You're not going to want to use that of like you and the Earth. Like, how much force do you impart on the Earth? And the answer is pretty much 0. Like it's 0,
really close to 0.
0. Like, I mean, you are not going to cause the Earth to move towards you. Now, what is interesting is if you look at the force of Jupiter on the sun, like the sun is massive, but so is Jupiter. And so the fact that Jupiter actually does affect the position of the sun, depending on where it is pretty cool. So we are way far away from where we're supposed to be, but this is exciting stuff. I don't think anyone's nodding off right now. Well, maybe, but anyway. Let's come back to this, like pull up a rope. Like how much work do you do pulling up a rope? So let me come down here and at least put in what the gravity is. It's going to be measured in meters per second squared. And I'm not going to be real picky on this. You could say it's 10. It's close enough, right? No, it's not close enough. What about 9.8? Well, no. What about 9.81? Well, that's actually a rounding too. 9.806. I don't. This is all going to be approximate anyway, and we can round to the nearest joule. So I'm going to use that as my gravity here. So if you looked at just the rope itself, let me just sort of put it up here. If you look at just the rope itself, forget that it's hanging, forget it's anything. What is like the force on the rope in newtons? So in newtons, this would be 9.8 meters per second, so that's per second squared, times the density of the rope, 0.066. That's measured in kilograms for every meter. And then the length of the rope is 60. So that's in meters. So you know that in order to get newtons, you need kilogram per meter, or meter per second squared. So you can see when you multiply all these things out, you do have your kilogram, one of the meters things will cancel out, and you'll get your kilogram per meter squared. And so that's approximately 38.8 newtons. So the rope itself is that. So the point is if the rope was entirely coiled up into a ball that was lying on the ground, and you lifted it 60 meters up, so maybe I can sort of put this off to the side, that if you're on this cliff and the rope is completely down here, and somehow magically you wanted to lift that rope all the way up 60 meters, you could just straight up do work equals 38.8 times 60, and you'd be done. You'd be done. Because you're taking the entire rope, which is, this is newtons, 38.8 newtons, you're multiplying it by the 60 meters, and you would be done. You would be done. Here's the problem. Here's where calculus comes into play. As you're pulling this rope in, what's happening? So if you pull 1 meter in, then will have lifted the entire rope 1 meter. And I hope that makes sense. Now, how much rope is still hanging? The answer is 59 meters would still be hanging. So now you need to lift that 59 meters 1 more meter. So that original first meter you pulled in is already done. You don't have to worry about that anymore. So you're lifting 61 meter, and then you're done with the top meter. Then you have 59 left. So you take that 59, you raise it up 1 meter, and you're done. And therefore, you have to do the other 58. Then you have to lift the other 57, then you have to lift the other 58. So by the time you're near the end, you only have a little 3 meter rope that you lift, and then you have 2 meters that's left, and then you have 1 meter that's left. And so you don't always have to do all of the 38.8 meters, all of the 60 meter distance.
So if this is just the force of just the rope alone, correct?
Yeah, so if you just had the,
Okay.
you're lifting the entire rope as a bundle up 60 meters, that's how much work you would be doing. Come back over here and look at the picture. This first meter right here, how far do you have to lift that first meter? And the answer is you only have to lift it 1 meter and then you're done. That part doesn't have to be lifted anymore. It's really close to the top. This bottom meter down here, you have to lift it all 60 meters all the way up. So the first meter, you only have to lift 1 meter. The second 1 meter, you have to lift it 2, because you have to lift it all the way up. It's down here at like
Okay.
58.
Okay.
You have to do a lot less work on the top part of the rope than you do on the bottom part of the rope. So it's going to vary depending on where you are. That's the point.
Okay.
So if you break this up, say if you broke it up into,
So the density, what about the density though? You were given the density, correct?
yeah, I mean, all this stuff is, the only thing that changes is how far you have to move.
Okay. And then you converted that to 0.66 kilograms per meter. Okay.
Yeah. So
0.0666.
So really, the idea is to break this up into 60 pieces, figure out each amount of work that you have to do on each of those, and then add them up. So this is kind of like a Riemann sum. You chop it into these little strips of 1 meter. You approximate the work, and then you add up all, like work 1, work 2, work 3, all the way up through work 60. You add all of those up, and that will be a good approximation for the amount of work. Now, how did you do that in a Riemann sum? 1 meter might be too big, so let's chop it into centimeters and do the work for all 6,000 centimeters. Add those up, and that'll be a better approximation because you've made it a finer and finer amount, just like you did in a Riemann sum. And then in the end, you're going to take a limit, and this will turn into an integral. And I think just giving you the formula for that is like, what? Hold up, where did that come from? It's confusing. It's confusing. So I think this idea of just taking a basic problem where you take the work, which is the newtons times how far you move it, and just do that repeatedly for each section, you'll be in good shape. So let me put this on the next slide. So here's the idea: is you have to move the entire rope, has to move 1 meter. So you have to lift the entire rope up 1 meter for sure. So how much work did you do on that? Well, the work that you did on that would be, well, you have to go, let's see, I take the entire rope, so I need the newtons times the meter that I've done there. So I'll get 60, I get the same calculation, 60 times 0.66 times 9.8 meters, and then I need to move that one meter up. So it's like the newtons and the meter, and that'll be how much work it is to move the entire rope up 1 meter. Okay, so now you've moved it up 1 meter, the leftover is 59 meters that's still hanging. So I have to move that up. So let's move this up. Let's move that up 1 more meter. Like, okay, how much work does it take to do that? Well, I'm moving it 1 meter. So that's my distance here. This should actually be d instead of 1 meter. Newtons times distance. So I'm still going to move it 1 meter, but how much do I have to do? Well, it's 9.8 for the gravity, it's 0.066 for the density, but now I only have 59 meters of rope left to move. And so that will be the work to move the remaining 59 up 1 more meter. So now how much is left over that I still need to pick up? 58. So 1 meter has been reeled in, another meter is reeled in, they're sitting on the ground. I now have to pull up the remaining 58. And I just repeat this process. The work for that part will be, now I have to move the rope 58. I have 58, I'm not moving it 58. I have 58 meters left of rope, still has the same density, still has the same gravity, and I will hit 1 meter. So it's like 1 meter, 1 meter, 1 meter, and each time the rope is getting shorter and shorter and shorter. So the amount of work I have to do for that 1 meter is less because there's less rope hanging. And that's about as simply as I can describe it. If I do the leftover, I've got 57 meters. This will be the last one I do. So there's 57 meters still left hanging. And I still move that 1 meter. And then all the way down until I have only 1 meter of rope left hanging. And the work on that part will be, well, I've got 1 meter of rope left. It still has the same density and 9.8 meters per second squared on it. And I move it 1 meter. And that's like work on the first meter, second meter, third meter. So we can call this like work 1, work 2, work 3, 4, all the way down to work 6. Hang on. And then I add them up. I add them up. And so the total work will be work 1 plus work 60. And again, this will be an approximation to the actual answer. All right, go ahead.
2 things not to mention that. 1, why do you need to add up all the work for each individual one? Because moving the whole entire rope up 1 meter, couldn't you just say like you move the entire rope 60 meters and then just find it through there? Like, what's stopping you from just doing that? Just saying, entire rope moves 60 meters, enter in the work formula, and just plug and play. Does any really stop you from doing that?
When you're reeling in a rope, does the top part of the rope actually have to move 60 meters?
No.
Right.
Okay. It's applying that constant to all of them, even though it, okay, I understand.
Yeah. The only part of the rope that actually moves 60 meters is the very end.
Mm.
The stuff at the top is going to move a lot less. And in fact, this is one way to think about it, where it's how much rope is left, and you move it 1 meter and then take it away, and then you remove the entire rope. If you wanted to think about it as that top meter, I could have just put a 1 here and moved it 60 meters. So the bottom 1 meter moves 60 meters. How about the next one up? How much does that 1 meter of rope have to move? Well, it doesn't have to move 60 because it's only 59 meters away, so I move it 59. So it's kind of like reversing the position of these. So I think about how much rope is left and move 1 meter of that at a time, or take the rope, break it into 1 meter sections and figure out what the work is on all of those. And the order of just which one goes with the force and which one goes with the distance will be reversed.
We're going to have to use Raymond sums for this, aren't we? Or Riemann sums.
That's exactly what this is. This is a Riemann sum.
Yeah, I was going to say, kind of knows the pattern there.
Yeah.
Because you start from 1, you move slowly up more and more and more. But would you have to include that part where the entire rope moves on 1 meter as well? Or could you just exclude that?
Well, on the very end.
Yeah. No, I mean for the first part. I meant, sorry.
Well, the point of this is look at what happened. What is happening each time is it's going down by 1, right? This is going down by 1. That's going down by 1. That's going down by 1. Everything goes down by 1. This 1 meter right here is really how you did your chopping. This is how wide your rope is. So this would be your delta X in the Riemann sum. So this is like your delta X. This is like going to be a formula that I'm going to want to get. Instead of going down by 1, what happens if this delta X was half a meter? Suppose that was half a meter. Then my delta X would be half a meter. What would happen on the front? It would go 60, then 59 and a half, then 59, then 58 and a half, and then 58. I'd have to break it up into 200 pieces and work all of these things out. But the point is, if you start to see these patterns in here, here's exactly what the pattern is. Instead of using a sum, we can use a limit and use an integral. And this 60, 59, 58, 57 is going down by however much we chopped it off. So we're subtracting off the X. In this case, it's either 1, or it could be a half, or it could be a centimeter, it could be a millimeter. So the 60 minus X is taking into account this fact that 60 is going down. The other parts are just it's the density doesn't change. So that's just the density. The 9.8 doesn't change. And the delta X becomes dx. And now I'm integrating it over the entire length of the rope. And that right there is the exact answer for the work for the entire rope. So there you go. It's like basically infinitely many, chopping this into little pieces, figuring out the work on each of those by just doing force times distance, and then adding them up, and you get down to that point. So it does take a little while to figure out that pattern, but anyway, that's it. That is the formula. We wanted to, if you want to do for completion's sake, what this looks like: 0 to 60. 60 minus X, 0.066, 9.8 dx. And if you work that out, it's a really easy integral. I think you can do that. But if you wanted to confirm your answer was correct, it turns out to be 1,000. What am I doing? 1,164.24 joules. I think that's an exact answer if you use 9.8.
Why the integral? Well, I mean, I understand it's connected to Riemann sums, but why not just use Riemann sums to begin with? It just seems simpler. Like if you just put n is 60, I is 1, just kind of create a formula and go from there, couldn't you?
You're saying the Riemann sums are easier?
Yeah, I mean, it just seems easier. It sounds like it would just be easier conceptually.
Your answer, I agree. Your answer would be close. It would be close. If you only care about approximation, that's fine. The other thing to note is that means you're going to have to work out 60 of these things and add them up.
Oh, okay, never mind. I understand.
Right. The other thing is this: technically, even within a 1 meter of rope, right there, the top of this rope, there's going to be less work that you need to do at the top of the rope than there is at the bottom of the rope, because you technically are going to have to move it a little bit more. We've kind of pretended like this is one condensed thing, and everything moves up. So all the stuff we were doing was again also an approximation. So the distance being 1 meter is like, well, technically that's true, but when you've moved it in 30 centimeters, you know, the top is done and you do no more work. You only have to work on the bottom 70 centimeters. But I think that the approximation ends up being fairly close. So if you want to chop it into 6,000 centimeters and work all of those out, you could. And probably in that case, if you did, you'd get pretty close to this, you know, 1,164 joules. But I don't want to add up 6,000 things. Maybe you can do it in Excel, something like that. But yeah, you're right. You're right. Conceptual, and that's what you should always do: is take it, make it conceptual to you, so that if you do have to use an integral, maybe it makes sense. This should be like, okay, that's the density. That does make sense. This is gravity. Okay, that makes sense because I'm going to need to get newtons in here. This right here really is like the amount of rope left hanging after X meters have been reeled in. So you know that you're not going to have to do any more work to rope that's already been reeled in and sitting at the ground at your feet on top of the cliff. You're only going to have to do work on the stuff that's left. The dx really comes in as basically how fine you're chopping up the rope in order to get the ream on. Conceptually. So these are all just conceptual things. This 0 to 60. Anytime you see an integral, you really can think of this as I'm going to be adding up every part of that 60 meter rope. Whether I chop it into 1 meter sections, I chop it into centimeter sections, I chop it into nanometer sections. It might be overkill if you did that. But that's where all of the pieces come into play. Now, before we take a break, because I know we've been talking here a while, let me say this. If you knew that the rope was of a constant density all the way out, there is something called the center of mass. And maybe you know that what the center of mass means. If you have a 60 meter rope, then where is the center of the rope? And the answer is right in the middle. As long as it's uniform all the way through, and the center of mass is right in the middle, 30 meters on top, 30 meters on the bottom. So this is a trick. What you can do is just pretend that the entire rope has been shrunk down to just the center of the mass. So the stuff at the top, you know, that's 1 meter off from the top is balanced by the one that's 59 meters from the top. 2 meters from the top is balanced by 58 meters from the top. So if you wanted to, if you condensed the rope to the center of mass, so here, then you could actually just do the entire work formula by doing this. It would be, you're moving the rope, which is 60 meters long, and you are still having the density 0.66 kilograms per meter. You're still doing 9.8, but then you can just pretend that you're moving the entire rope 30 meters. You're moving the center of mass, which the entire rope has been condensed down. Now you're back at that original problem. You're just moving a rock effectively one distance. You don't have to worry about chopping it up because you condensed it all down to one thing. So really it's just like newtons times distance, and that will also give you 1164.24 joules without having to do any integrals at all, but using the center of mass. So that's, if you've seen that in physics before, or even if you haven't, that's the idea. The uniform object can be condensed into one like point mass that has this Newton value and multiplied by its distance. Because again, work is just force times distance. So anyway, yeah. Take a break. Definitely need a drink here. and we'll come back at say 10:40-ish or so. So let's do that, and then we can do a little bit more. Well, 7.6 may be pushed off and see how much questions we have. So anyway, quick break. See you in about 5 or 6 minutes.